Let's have the discussion about t-distribution and confidence intervals.
The t-distribution was formulated in 1908 by an Irish brewing employee named William S. Gossett. Gossett was involved in researching new methods of manufacturing beer. Brewing employees were not allowed to publish the result, so that Gossett published his finding using his pen name as student. Hence, the t-distribution is sometimes called student's t-distribution. So now, let's talk about the t-distribution. So when we say t-distribution, it represents the standardized distances of sample means to the population mean, wherein the population standard deviation is unknown, and the observations come from a normally distributed population. And these are the following characteristics of t-distribution. Based on the figure on the right side, the mean, median, and mode are equal to 0 and are located at the center of the distribution. Number 2, it is bell-shaped. Number 3, it is symmetric about the mean. Number 4, the curve never touches the x-axis. That's what we call asymptotic. Number 5, the variance is greater than 1. Always remember that the variance of t-distribution is always greater than 1, although it is close to 1 when there are many degrees of freedom. With infinite degrees of freedom, the t-distribution is the same as the normal distribution. Later on this video, we will find out the reason why 6 and 7 characteristic of t-distribution is evident. Now, let's differentiate z-score to t-score, and this formula represents z-score, where z is the z-value, mu is the population mean, sigma is the population standard deviation, n is the sample size, and x bar is the sample mean. On the other hand, this formula represents t-score, where t is the t-value, mu is the population mean, s is the sample standard deviation, n is the sample size, and x bar is the sample mean. Take note, okay, you will use the z-score if and only if the given sample size is 30 and above, wherein the population standard deviation is known. Otherwise, you will use t-score of the given sample size is less than 30, wherein the population standard deviation is unknown. So we will go now to the degrees of freedom. So when we say degrees of freedom are the number of values that are free to vary after a sample statistics has been computed, and they tell the researchers which specific curve to use when a distribution consists of a family of curves. To easily understand the idea of degrees of freedom, let's have an illustration of degrees of freedom in a normal curve using our example. If your sample size is 6, then the degree of freedom is calculated by subtracting 1 from the sample size, so 6 minus 1 is equal to 5. And 5 now is your degree of freedom. What if the sample size is 21? Again, same procedure in our first example, subtract 1 from the sample size and it will become 21 minus 1 is equal to 20, and 20 is your degree of freedom. As you can see on the illustration, as you increase the sample size, the curve approaches the normal distribution, which justify the characteristics of the distribution. Now, let's find the critical value if the confidence interval and sample size is given. For example, find the critical value for a 95% confidence interval when the sample size is 18. So these are the steps in finding the critical value in a t-table. First step, locate the degrees of freedom to the first column and its corresponding level at the bottom row. Second step, locate 17 on the first column and 95% on the last row. And third step, locate the value that is aligned to both degree of freedom and confidence level. Therefore, the critical value for 95% confidence interval when the sample size is 18 is 2.110. Let's have now another example. Find critical value for 98% confidence interval when the sample size is 10. Again, same procedure in example number 1, we should follow the steps in example number 1, and we'll find out the critical value of 98% confidence interval with a sample size of 10. Therefore, the critical value for 98% confidence interval when the sample size is 10 is 2.821. Take note, we use T sub A over 2 because we are pertaining to two-tailed that uses both positive and negative tails of the distribution.
In statistics, we know that the population parameter is unknowable. Now, in this particular lesson on confidence interval, we will learn techniques on how we can estimate the true population mean of the population based on our samples. And this is part of our lesson for today, wherein we're trying to judge the population based on our samples. Let's say this population parameter contains all the dogs in the Philippines, and we're interested to know the actual average weight of all the dogs in the population. In order to do that, we know that the population mean is unknowable, and there's no we can find the actual value or the exact value of the average weight of all the dogs in the population. So what we're going to do is to take some samples from the population to give a better judgment or estimation. Let's say our first sample is I took 30 dogs from the population parameter, and from these 30 dogs, we weighted them and took the average and computed for the average weight of these 30 dogs is 3.2 pounds. Then we take another example which is 231 with average weight of 4.1 pounds. Now we take another sample which is 356 with average weight of 5.7 pounds. Now if you'll notice, we are basically estimating or trying to find the estimated value of the population mean based on our samples. Now in this topic, we will learn techniques on how to find the range of values that will capture the true value of the population mean using our samples, and that's what we call confidence interval. Estimated range of values which likely to include the unknown population parameter at some confidence level, and also constructed from sample data, meaning without the sample data, we can't estimate the range of values of the population parameter. The width of confidence interval, where C is the confidence level, When we say confidence level, it is the percentage of times you expect to reproduce an estimate between upper and lower limits. Z sub alpha over 2 represent the critical value. It is a line on a graph that split the graph into two sections, which are two-tailed region, and they are symmetrical to each other. The population parameter located at the origin of the graph, and alpha represent the significance level. Significance level is a measure of the strength of the evidence that must be present in your sample. The formula of finding the alpha is alpha is equal to 1 minus confidence level. There are three common confidence levels, which are 90%, 95%, and 99%. The critical value of 90% is 1.645, 95% is 1.960, and 99% is 2.576. They are common confidence level because they are commonly agreed to be used by most statisticians and data analysts. Let's proceed in finding the critical values given the confidence level of 70%. Find the critical value. In order to solve this problem, we have steps. Step 1. Use the formula of alpha. Step 2. Substitute the given confidence level to the formula. Step 3. Subtract the given confidence level from the total area, then the result alpha is 0.3. Step 4. Divide the result alpha into 2, then the result is 0.15. Step 5. Find the corresponding z-score using z-table from the result of alpha over 2, wherein the nearest area of 0.15 is located at negative z-table, which is 0.15151, with corresponding z-score of negative 1.03. Since negative 1.03 is symmetrical to positive 1.03, therefore, our critical value is positive 1.03, or z sub 0.15 is equal to positive 1.03. Then step 6, sketch a curve by locating the population mean at the origin with the confidence level above it. The result critical value located on the upper and lower limits. For example number 2, with given confidence level of 80%, find the critical value. In order for us to solve this problem, just apply all the steps used in example number 1. Therefore, our critical value is positive 1.28, or z sub 0.1 is equal to positive 1.28. And the illustration of the graph is this. Estimation is the process of estimating the value of a parameter from information obtained from a sample. Meaning, without a sample, we cannot estimate the actual value of parameter. An interval estimate of a parameter is an interval or a range of values used to estimate the parameter. This estimate may or may not contain the value of parameter being estimated. Point estimation is a single value estimate for a population parameter, meaning the best unbiased point estimate for the population mean is the sample mean. Now, let's proceed in confidence interval for population mean when population standard deviation is known. Margin of error, is the range of values below and above the sample statistics in a confidence interval. For the estimation of the population mean, the margin of error is calculated with this formula, where C sub alpha over 2 is the critical values, alpha is the level of significance, standard deviation over square root of sample size is the standard error, plus the product of critical values and standard error will be the upper limit, minus the product of critical values and standard error is the lower limit. The formula for the confidence interval of the mean for the specific alpha is population mean is greater than the difference between sample mean and lower limit but less than the sum of sample mean and upper limit, or the population mean is greater than the difference between sample mean and margin of error but less than the sum of sample mean and margin of error. Now, let's proceed in solving confidence interval for population mean when population standard deviation is known. A random sample of 55 students' scores on an exam has a mean of 45. The students' scores on an exam are normally distributed with a population standard deviation of 4.7. Estimate the population mean with A. 75% confidence level and letter B. 85% confidence level. Let's start with letter A, 75% confidence level. In order for us to solve this problem, the first thing to do is to identify the given, which are sample size is equal to 55, sample mean is equal to 45, population standard deviation is 4.7, standard error is 4.7 over square root of 55, and confidence level is 75% or 0.75. The question is, what will be the value of critical value and the margin of error, so that we can estimate the actual value of the population parameter. Second is use the formula of alpha. Third is substitute the given confidence level to the formula. Fourth is subtract the given confidence level from the total area, then the result is 0.25. Fifth is divide the result alpha into 2, and then the result is 0.125. Sixth is find the corresponding z-score using z-table from the result of alpha over 2, wherein the nearest area of 0.125 is located at negative z-table, which is 0.12507, with corresponding z-score of negative 1.15. Since negative 1.15 is symmetrical to positive 1.15, therefore, our critical value is positive 1.15 or z sub 0.125 is equal to positive 1.15. Seventh is solve for the margin of error. Then, substitute the result critical value and standard error to the formula. Therefore, our margin of error is 0.73. Then 8 is solve for lower limit and upper limit. Lower limit is difference between sample mean and margin of error. Therefore, our lower limit is 44.27. Then upper limit is the sum of sample mean and margin of error. Therefore, our upper limit is 45.73. Ninth is substitute the result lower limit and upper limit to the formula of confidence interval. Therefore, the answer is population mean is greater than 44.27 but less than 45.73. Tenth is interpret the result. Based on the normal curve, we are 75% confident that the population mean score is between 44.27 and 45.73 based on a sample of 55 students' score. For example number 3, letter B, with 85% confidence level, in order for us to solve this problem, just apply all the steps used in example number 3, letter A, so that we have these results.
If the population standard deviation is unknown and the sample size is less than 30, confidence interval for population mean can be constructed based on the student distribution, provided that the population from which the random sample was obtained is normally distributed. So, this is the formula that we'll be going to use in finding confidence interval for the mean when population standard deviation is unknown and n is less than 30, where x bar is the sample mean, alpha is the level of significance, s is the sample standard deviation, and n is the sample size, and s over square root of n is the standard error. By this, we will proceed to example number 1. Suppose that a random sample of 8 students got the following grades in statistics with the mean of 87 and standard deviation of 5.66. Find the 99% confidence interval of the mean time. Assume the variable is normally distributed. So, these are the step or easiest way to solve a confidence interval for the mean when population standard deviation is unknown and n is less than 30. So first step, find the given. Second step, get the critical value of this problem. Again, by using this t-table, we will follow the steps on how to get the critical value. So, find the critical value for 99% confidence interval when the sample size is 8. And here are the steps in finding the critical value on a t-table. So again, locate the degrees of freedom to the first column and its corresponding level at the bottom row. Next is locate 7 on the first column and 99% on the last row. And last is locate the value that is aligned to both degree of freedom and confidence level. Therefore, the critical value for 99% confidence interval when the sample size is 8 is 3.499. By substituting the corresponding value to the formula, we'll have x bar minus t sub alpha over 2 multiplied by s over square root of n. So, 87 minus 3.499 multiplied by 5.66 divided by the square root of 8. By using the rule of GEMDAS, you will get 80. Same goes on the other side. We have the form of x bar plus t sub a over 2 multiplied by s over square root of n. So again, by Jemdas rule, we have the value of 94. Okay? So the specific confidence interval is the mean is greater than 80 but less than 94. Based on the illustration, we can conclude that a 99 confidence interval for the true average grade in statistics implies that you are 99 confident that the true average score in statistics is between 80 and 90. For example number 2, in order for us to solve this problem, just apply all the steps used in example number 1. So we have this given.